this lecture, we begin applying what we've learned about the measures of central tendency and variance, probability distributions, and the normal distribution to specific scenarios. In the previous lecture segment, I introduced the inflection point as the point on a graph where the curvature of the line changes from convex to concave. Convex curves have the hump on top so that it looks like a hill, whereas concave curves have a trough. It is important for you to be able to visualize the inflection point on a graph because for a normal curve, it marks off exactly one standard deviation from the mean. Trace the blue line of this curve. Now, imagine you're an itty-bitty bug crawling down this hill. You will feel the path change at the inflection point, so it no longer feels like you're going straight down, but instead like you're coasting. Then, once you find that point, mark the inflection point and draw a vertical line down to the horizontal axis. Now, note the distance between the solid black line, the direct center of the graph, where the mean and the median are equal, to the dotted line. This is the width of one standard deviation on the curve. Mark off a few standard deviations to the left and right of the mean. Let's try more. Remember, the standard deviation value is a reflection of how spread out the data are. For large standard deviation values, the curve appears squished down or stretched from left to right. For small standard deviation values, the curve is tall and skinny. Pause the video and see if you can successfully identify the inflection point in each graph and mark off 2 to 3 standard deviations to the right and left of the mean. If I were marking these, I think the inflection point for this guy is right about there, which means this is the width of a standard deviation for the whole curve. All I have to do now is get approximately the same distance on either side to set up the standard deviation markings. For the narrow curve, I feel that the little inflection point is right about there. So now I see I could set up my distribution like so. They're not perfect, but they don't have to be perfect. We're not going to actually use these to measure anything. We're going to use it to make approximations. Now, let's add some actual numbers to our distributions. In 2002, the SAT verbal scores were normally distributed with a mean of 504 and a standard deviation of 111. Because the SAT is administered and scored by one company, the population parameters of the full data set are known. That's why we're using the Greek letters mu and sigma, both lowercase, to designate the mean and standard deviation respectively. On the horizontal axis, the mean is directly in the center. Then add 111 to get 615, 111, which is plus 1 standard deviation from the mean. Add another 111, 615 plus 111, 726. And this is the plus 2 standard deviations above the mean value. To go to the left of the mean, simply subtract the standard deviation value from 504. 504 is the mean, minus 111 is 393. 393 is miss 1 standard deviation from the mean, minus meaning it's below it. You could do this again and come with the next value, 282, which is minus 2 standard deviations from the mean. Practice setting up the normal distribution if the mean is 50 and the standard deviation is 10. If the mean is 50, that value goes in the center, and then adding 10 for each standard deviation marking and subtracting to go to the left. Whoops, not minus 40, it was simply minus 10 to get 40. 30 and 20. Now use the values of 620 and 88 as the mean and standard deviation respectively. Pause the recording and then check your own work. $620 in the center, 620 plus 88 is 708. Add another 88, 796. And one more to the right, add another 88, and we get 884. Now let's go the other direction. 620 minus 88 is 532. Subtract another 88, and you get 444. And one more, subtract 88. You get 356. Okay, last time. In this distribution, set the mean at 14.5 and the standard deviation at 0.5. Pause it one more time and then check back to see how you did. Mean goes directly in the middle, 14.5. Ooh, I'm going to change colors. 14.5, and I want to go to the right. I'm adding a half, so that should be pretty easy to just set up. I go 15.0, 15.5, and 16.0 to the right, and subtracting 14.0, 13.5, and finally 13. So I could say that on this distribution, the value that is 3 standard deviations above the mean is, let's see, plus 1, plus 2, plus 3 is 16. One of the convenient aspects of the normal distribution is that the areas under the curve, regardless of the mean and standard deviation, are the same. Approximately 68% of all observations fall within plus or minus 1 standard deviation of the mean, and then approximately 95% fall within plus or minus 2 standard deviations of the mean, and 99.7% of all observations fall within plus or minus 3 standard deviations of the mean. This is what we call the 68-95-99.7 rule. And it's wonderful because it allows us to quickly determine the number of observations lying between two specific scores. If we break up the 68, 95, 99.7 values to match each symmetrical portion of the graph, the values are 2%, 14%, 34%, and then because it's perfectly symmetrical, we just go back. 34%, 14%, and 2%. I remember the first two percentages, 2 and 14, because the number 2-14 corresponds to Valentine's Day. Then, remembering that half of the graph, so from the direct middle, ooh, that's a horrible line, but you get it. Half of that graph is 50%, so if you can take 50 minus 2 plus 14 is 16, you get 34%, which is the third value. The x-axis values, in this case -3, -2, -1, 1, 2, and 3, represent the plus or minus standard deviations from the mean for the normal curve. Let's apply the 68, 95, 99.7 rule to a specific scenario. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, with a mean of 266 and a standard deviation of 16 days. This notation here says n for normal, and then the mean is listed first, comma, the standard deviation. This is a standard set of shorthand for discussing the shape of a curve. Let's begin by setting up our curve, even before we read the rest of it. Let's go ahead and say, okay, the mean is 266. I'm going to add 16, gives me 282. Again, 298. Again, 314, and finally 330. That's to the right-hand side. Now let's go left. 266 minus 16 is 250. Subtract another 16, 234, then another 217, and finally 201. In the first question, you are asked to state the minimum and maximum number of days associated with the middle 95% of all pregnancies. 95% corresponds to plus or minus 2 standard deviations. So the lower boundary is 234, and the upper boundary is 298, because those mark plus or minus 2 standard deviations from the mean, which is 95% of all observations. This means that approximately 95% of all human pregnancies from conception to birth last somewhere between 234 to 298 days. The second question asks only about the shortest 2% of pregnancies. This corresponds to the small area underneath the curve, beginning at minus 2 standard deviations to the left, so right here, and extending to the left. From a couple of slides ago, or actually just the last slide, remember we said that we could split up the percentages under the curve using 2, 14, 34, 34, 14, 2. for the approximate percentages under the curve for plus or minus 2 standard deviations from the mean. Therefore, the maximum value for the number of days necessary to remain in this bottom or lowest proportion of the graph is 234 days. Thus, any pregnancy that lasts 234 days or less would be classified as being in the shortest 2% of all human pregnancies from conception to birth. Let's work another example. In this scenario, scores on an exam fit a normal distribution with a mean of 68 and a standard deviation of 9. Set up the distribution first. 68 is in the middle. Going to the right by adding 9 each time gives us 77,